All right, in the last sections we started talking about frames, right? The idea is that a frame is also made out of members that are connected at points, just like a truss. But unlike a truss, the forces can now act anywhere on the members, right? Remember, on the trusses, they could only work at the joints. And we said there's two different types of frames. There's the collapsible frame, where if I take any support away, the frame will deform, right? So we had kind of the tent kind of a thing. If I take one of these supports away, the whole thing just flattens down. The other one was the non-collapsible frame. There, even if the whole thing changes if I take a support away, it will move, but the overall shape will stay the same. And so what we're going to do next is we're going to do two examples. The first one is going to be an example for a collapsible frame, and then later on we'll do another one for a non-collapsible frame. So here's our example. We have, the same as that we looked at already. Now we have two members, A to B and B to C. We have two supports, one at A, one at C. Both of those are hinges, and then we have two loads acting on it. And we now want to know what are the support reactions and what are the forces inside of these pins. And so we found that we can create three different free body diagrams here. Right? We can take one for the entire system, and then we can take partial ones. So let's just draw those three free body diagrams. So we'll have a bar going up, and the one coming down is supposed to be a little longer. We can say we have at A, there was a support, a hinge. So we have a Y and a X. At C, we also have a hinge. So we have CY and CX, and then we have our two loads. And the load here, which is 7 kilonewton, and the load over here, which is 14 kilonewton. And then let's do a coordinate system, X and Y. And so now we can think about this. Can we get all of our support reactions? Well, we have 1, 2, 3, 4 unknowns. So no, we can't get all of our support reactions. That means we need our other two free body diagrams. So we do the from A to B, and let's put A, B, C in there. So now we are. Let's do A, B. Right there. We'll have our support reactions at A going the same direction as on our overall free body diagram. And then AY. The load, 7 kilonewton. And now we have to take this pin apart. Remember, we get two forces, or a force in our direction. We do two forces, so we have BX and BY. Let's do BX positive in this direction, and BY positive upward. I just want to double check that I'm doing the same in the notes so that it's easier to follow. Yeah, BY upward. So that'd be one. Now we have 4 unknowns and 3 equations, so we can't rely on that one alone either. So let's do the third one. We have our, let's do a B. That will be, let's put the forces in first. So we have our BX in that direction because we have the to the right there, and then downwards for BY. And then our two support reactions, we had CY upward and CX to the left. And now we can put our names on this. That was B, and that was C. Again, alone on this one, we can't get anything either. But if we just take these two together, we have 1, 2, 3, 4, 5, 6 unknowns. We could do 6 equations and solve it. Now, sometimes it's easier to also take the entire free body diagram into account, right? If you think about it on this case, if I did a moment about point A, I would have 2 unknowns. If I do sum of X, I have some 2. I have 2. If I do sum of forces in the Y direction, I have 2. And if I do it around some moments around B as well, and the same over here, right? So I would, in none of these cases would I get a single equation with a single unknown. So it's solvable, but I might have like a fairly a nasty system that I have to work with. So what I would suggest is that we go to the full system first and get as much as we can do there, right? So because if I can get a y and a c just by doing the sum of moments. So let's say full system, and we'll do sum of forces, sum of moments. I'll change this to point C. Around point C is equal to 0. Let's see what we get around point C. So we get AY turning clockwise at 7 meters. So minus AY times 7 meters. I get this 7 kilonewton going positive, and it is halfway in there. So it's 4 plus 3.5 is 5.5. So plus 7 kilonewton times 5.5 meters. That's there. And then I only have this one left, right? And that is turning also counterclockwise, so positive. So plus 14 kilonewton times, what's that height? 1.5 meters. And then C, of course, there's nothing there because I'm doing the moment about C. So I can solve that for AY. So this was negative, so the signs all stay the same. So I have 7 meters times 7 kilonewtons. Go back. That's the 7 meters from over there. 7 kilonewton times 5.5 meters plus 14 kilonewton times 1.5 meters. All that divided by 7 meters. And if I go through that, I get 8.5 kilonewton. 8.5 kilonewton comes out positive. So AY must be pointing upward. So I had upward, positive there. So now I have AY. So let's get CY basically the same way. So sum of moments about point A is equal to 0. Start over here. So I have my CY now positive. So CY times 7 meters. There. That's the whole 7 meters. Then my 14, I'm going about A now. So that is still going counterclockwise. So I have plus 14 kilonewton, and that height is still 1.5 meters. 1.5 meters. And then the last I'll have is my 7 newtons. That is now going clockwise, and it's 1.5 meters. So minus 7 kilonewton times 1.5 meters. All right, I can solve all this for CY. Signs here have to change. So that is 7 kilonewton times 1.5 meters minus 7. Nope, not minus 7 meters, the wrong one. Minus 14 kilonewton times 1.5 meters divided by 7 meters. And that gives me minus 1.5 kilonewton for CY. So that means it is positive going downward. All right, so now I have AY and CY. CAX, I can find that AX and CX are related, but I can't find any, so let's wait with that. So what could I do? I could go to my member here and just do a moment about B, because then the only unknown is going to be AX, so I can find AX. So let's say member AB. Member AB, sum of moments around point B, I think it was. Let's go back. Yes, about B. All right, so what do we get in B? We get AY going clockwise, and distance is 3 meters. So minus AY times 3 meters. AY times 3 meters. Then we get AX going counterclockwise, and it is 3 meters. So plus AX times 3 meters. AX times 3 meters. And then what else? Our 7 newtons is going clockwise. So plus 1.5 times 7. So plus 7 kilonewton times 1.5 meters. All right. We can solve that for AX is what we're looking for. So I have to flip signs. So that would be AY times 3 meters minus 7 kilonewton times 1.5 meters divided by 3 meters. We can get the 8.5 from up there, plug that in, and that will give us 5 kilonewton. It was positive. We had positive to the right, so that goes back. All right, so now that we have that, we can go ahead and look for if we have AX, we can get BX, and if we have AY, we can get BY. So we can say sum of forces in the X direction is equal to 0. What do we get? We get AX plus BX. That's pretty straightforward. AX plus BX, that means BX is minus AX. AX, we said, was 5 kilonewton. So that's minus 5 kilonewton. Oh, that's good. And then now we're not going to put left or right on this one because point whichever direction we're looking from, right? So that doesn't help us necessarily. And then we can do Fy equal to 0. We have AY minus 7 plus BY. AY, not plus, but minus, it's pointing downward, minus 7 kilonewton plus BY. That means BY is 7 kilonewton minus AY. Let's see where it was. AY was 8.5 kilonewton. So that should be minus 1.5 kilonewton. 1.5 kilonewton. Very good. Now I could go over and do the same over here to find CX, but I also can go back to the main one and look there, right? If I just do the X direction on the full system, then I can get my CX as well. So we're back to the full system. Sum of forces in the X direction equal to 0. I have AX minus 14 minus CX. AX minus 14 kilonewton minus CX. That means CX is AX minus 14 kilonewton, and AX was 5 minus 14 would be, did I get the signs correctly here? CX negative? Yes. Yeah. So that gives me CX, not CY. So that would give me CX, what are we saying? Minus 9 kilonewton. This is a support reaction. We had it positive going inward with negative, so it's actually pointing outward. And with that, we have all our unknowns. Right? We have the four support reactions, I'm sorry, and the two up here. So that's all we have. Now we didn't use all of our equations. So we could use more equations, right? So we could say, for instance, if we do sum of forces on the full system going upward, so if we do sum of forces in the y direction, f of y equals 0, we get ay, cy, and minus 7. Let me just think. So ay is ay minus 7 kilonewton plus cy. ay is somewhere up here, 8.5. 8.5 kilonewton minus 7 kilonewton, not equal to, plus cy. Where's my cy? cy is minus 1.5. Minus 1.5 kilonewton. And that's equal to 0. So I know that this one is, gives us some confidence. Now we could go through and do even more of those, right? We could look over here. Oops, just realized. Forgot our load on this one. That's not good. Fortunately, we didn't need it. But we could look here, for instance, too, right? So I know that bx plus cx has to be 14. Where is my bx? So minus 5 and minus 9 is 14, so that fits. And again, we could do moments, we can do other ones, but we'll leave it with the one test for now. So this was an example of solving for the support reactions and the forces in the pins for a collapsible frame. So again, the idea is that we take our frame, we do the free body diagram of the entire frame, replace the supports by forces, and then we take the frame apart and then add forces where the pins are. Very important that the forces have to cancel each other out if I put them back together, right? So if bx to the right here has to be the left. If by is upward positive, it has to be downward positive on the other side. And then I just have to kind of see where my easiest equations are, and then I can go step by step to solve the entire thing.